else. We want to be able to say, I want this object and I want it here. I need to use it, so please go and fetch it. Once you're ready, you let me know and I'll use it. We want to have automatic caching, meaning that we want to say all this stuff is visible to me. It's your problem how you make that happen, but do that as fast as possible. Meaning, don't fetch it from the file instance drive you know about all the time, because that slows me down. Try and keep it as close to me as you can. And in that, which is the other point, same thing, we want the I/O activity to the lower tier of storage to be as little as possible, because so the model is that when you go and pull from disk, the bandwidth is infinite, meaning as soon as you find your thing, it takes 0 seconds to pull away as much data as you want. But the latency is infinite, meaning it takes forever to find it. And that models pretty well what standard filers do. If you buy, okay, our hard drive is 1 to 2 petabytes. Actually, we have 2 of those. So we have 2 petabytes of data to index across. It takes forever to find stuff. Even if you know the file path, it doesn't change anything. It's just somewhere lost. We have, I don't know, 3,000 hard drives in it. It's insane, right? So you can't say that I want it and it gets to you. That's what your workstation does. The filer will take some time. It may even go down between when you do a request and when it serves it. They do that. They get the request, they go down, they come back up, and then they serve it. It could be 3 days, but they do that. So, you know, you have to be able to deal with that. So, what did we do? Well, we stole an old idea. We implemented that. Well, not really, but. So, I'm serious. No, so, anyway, this picture is awesome. Yeah. I was barely walking when this was made. So, this is a printer. This machine is like this big. Serious piece of hardware. This is a punch card reader. Serious stuff, you know, it has little holes, you can stick them in little piles and then it reads through them. This doesn't have magnetic tape. It's a serious piece of hardware. That's the screen, this big. Beautiful. You know, 25 by 25 characters. So, that thing there, 48-bit of address space, same as the Pentium 4. Completely object-oriented. So, the system as hardware knows about 14 different object types. That's built in, same as ours know about bytes. And it has no file system. So everything is available. It's all flat. You don't know anything about where things are. That's their problem. So to do that, they built a relational database system inside the operating system, and everything was query-based. So, of course, they were designing a database system. That's DB2. These things here is now called AS400, or IBM Power Series, if you buy it today. They just renamed it last year. 30 years later, it's the same architecture. Interestingly, that's the first machine that had completely virtualized hardware. You don't see hardware in that machine. Never. You only talk to drivers. And you don't compile down to binary code that is executable. You compile down to what we would call now bytecode. Same as Java. But, you know, 15, 20 years there. So you compile to this intermediate representation, and then there is the loader that loads your program onto the hardware, takes care of compiling it down to whatever your hardware looks like. So program built in 1978 for that very machine still runs today on the Pentium 4s that you can buy from IBM as the IBM Power Series. It's the same. It's great. It's a little hard to do, but it's great. So, yeah. So, what do we get? Computer graphics. What we do is very similar to what everybody of you guys do. We do computer science. We do binary searches. We do, you know, linked lists, this kind of stuff. The classical computer science is what we do every day to do computer graphics advancement. We also talk to the NVIDIA guys to do OpenGL hardware acceleration stuff. But we mostly focus on, we know that we learned through very direct experience that making programs run faster means making them doing less things. And I'm not kidding, that's how you do it. So the really, really fast programs are more smart and they try to do less because doing less things is more reliable and takes less time. So it's not an inherently computer graphics problem, it's a standard computer science problem. Where do you store your things? What order are they? How do they interact with your caches? The other thing that we do is we do we are very open to the other communities of research, all of them, chemistry, physics, optics, medicine. We steal a lot. We did a lot of research in skin and humans, depicting humans. The guys that do medical analysis, you know, for tumor, for this kind of stuff, they did a lot of research of interaction between light and skin, light and various types of tissues. We read all of that. Well, not me, but we tried to read as much as that as it was feasible. And we make programs that simulate all that. And so if a genetist knows how to make a piece of light interact with a piece of skin and tell what it's made of, we do the same process backwards so that we can fool people into thinking that our pictures are actually made of flesh. We know that we don't know a ton of stuff, and actually it's not that we wouldn't like to know it, we just don't have the time to go and figure it out. But we have endless list of new things that we need to do. Charcoal. Nobody has a good solution to do charcoal or burning wood. Breaking wood is very hard. You know, I could go on forever. And you, any of you, can be part of that, as you know, as I would. I'm a mathematician. I do standard computer science, languages. I was trained in writing compilers. I did start with computer graphics. And then, you know, one thing led to another, and I landed into this. The field, the things you do every day for your, you know, adult life, if you will, is something that will take you away from where you thought you were going when you were 16. As many of you probably have realized by now. And that is cool. You know, I like it. It's been pretty good for me. And yeah, that's all I have to say today.